Good evening, everyone. Welcome to Stochastic Processes, class 7th lecture. Okay, so so first, let me do a recap of what we did last class. So in the last class, we saw two definitions of Poisson processes. So basically, Poisson process are processes where you try to model events happening, random events happening. So suppose you want to count you want to count the number of times that equipment can go to failure or can fail in a given year. That is random. So that modeling is done through Poisson processing. So Poisson processing is basically a counting process where you count the number of times that an event has occurred, and yeah, you say that given interval t, uh, the number of times that the event can occur is a Poisson distribution with the parameter lambda into t. So it is the time scale dependent. So at how much big the interval you're looking at, the expectation of more number of process, the expected number of um, arrivals would be linear. So it will be lambda into t times. So the two definitions that we saw were, one was where you had the tensor equal to 0 and independent increments, and the number of um, events happening in an interval t is Poisson distributed with parameter lambda t. The expectation of this term of the random variable is expectation of this random variable n t plus s minus ns is lambda t. So uh, the expected number of yeah, the expected number of events happening in that interval is linear in time. So nt, and then you also have this independent increment property that comes in because of the second one. So if you look at two non-intersecting time intervals, then the number of events happening in one time interval is independent of the number of events happening in the other time interval. Then there was the second definition of Poisson process, where we had that um, they have independent and stationary increment. Stationary increment means that they have the same distribution. The distribution doesn't change when you're looking at two different non-overlapping intervals of the same interval length. Then we saw that the probability of one event happening in a very small amount of time is lambda times into that small uh, interval duration plus an order of delta t, which as you decrease the length interval goes to 0, and the probability that number of events in a small interval is greater than 2 is of the order delta t. So what this basically means that two events can't happen simultaneously. There need to be a very minute amount of gap between those two. Then we saw, so we showed the equivalence of these two definitions in the last class, in the fifth class. In the sixth class, we saw uh, another way of defining Poisson process, that is to the inter-arrivals or the weighting distributions. So the inter-arrivals times are basically the distance, the time that that has gone through between two events that you're concerned about. So we saw that the distribution of inter-arrival times is an exponential distribution with parameter 1 by lambda. So probability yeah. So yeah, then we did the proof for why all the inter-arrival times are IID and distributed exponentially. Okay, then we showed that waiting times. So waiting times, or also known as, okay, I'll call as arrival times. Arrival times are the times where the ith of the nth event, where the nth event can occur, that is Sn. Sn is basically the sum of exponential random variables. Now, sum of exponential random variables, we showed them that they have the Erlang distribution. So this is the Erlang distribution. Um, uh, we also saw a bit about the shape parameter and the rate parameter. What defines the shape and what defines the rate? The shape parameter is defined by the distribution of which arrival you're talking about. If you're talking about the nth arrival, it will be the shape parameter would be of n. If you're talking about the n minus 1th parameter, the shape parameter would be n minus 1. Then we saw about order statistics. We saw about order statistics because, okay, so order statistics basically means that you have some IID random variables x1 to xn. These are random variables. You know the distribution of these random variables. But then when you sample, you know the distribution. When you sample from this distribution, uh, this n capital N random variables, you get some sample path. You get some sample path. Now this sample path, what you do is you arrange them in increasing order or in decreasing order. Mainly increasing order, we look at increasing orders. Then when you arrange them in increasing orders, you get an order statistics. And now this new data set, a new sample paths that you get, they follow a different distribution. That distribution is what we wanted to find out. So we saw that the distribution had the joint distribution of all those n variables had an n factorial term in the starting. This n factorial is due to the number of times that number of permutations that you can arrange them in comes here. So the joint distribution has an n factorial term here. So next we'll show is nt equal to n. So if I give you that in a time interval n events have occurred, then the arrival times or the waiting times of the n events that have occurred in that time interval is uniformly distributed. Uniformly distributed in the sense they have the same distribution as the order statistics corresponding to the n independent RV uniform distribution. So this theorem we'll do today. So okay, so we'll start first with we have a time axis t, and yeah, suppose this is the time slot that we're interested in. 0 to t, a small t interval. This is the time slot that we're interested in. Suppose I give you that capital N number of a smaller number of events have happened in this time interval. So they could be random. So let's say one event happened here, one event happened here, and one event happened here, and one event happened here. So now this is basically S1, this is S2, this is S3, and so on. So you'll have Sn. Now I want to find the joint distribution of S1, S2, and so on till Sn. This is what I'm interested in. So what I say is the distribution is equal to the order statistics of x1 to xn, where x1 to xn are IID uniform random variable. They can't be equal to just x1 to xn IID because once you say that, hello.
Yeah, Aniket, listen, problem with the university network, that's why I rejoined.
Oh, okay, okay, sure, no problem. Do you want me to repeat something?
Yeah, just 1 minute back.
Oh, okay, okay. So what I was saying is, so suppose you have the time scale t, and then you're looking at an interval of 0 to small t. In the 0 to small t interval, suppose I condition you that, okay, in the interval 0 to t, I know that small n number of events have occurred, and let them be random. Random events have occurred at random times. So now I have S1, S2, S3, S4 till Sn. Now I want to find the joint distribution of S1 to Sn. That is my main motive. So my claim is that the joint distribution of S1 to Sn is the order statistics of x1 to xn random variables, which are IID and have uniform distribution. Okay, so you know that S1 to Sn can't have just x1 to same distribution as x1 to xn, IID uniform distribution, because uh, once you fix S1, you always know that S2 would always be greater than or equal to S1. You know that S3 is always greater than or equal to S1 and both S2. Similarly, Sn is the greatest of them all. So there is, when you define S1 to Sn, there is particular order. S1 comes first, then S2, then S3, then Sn. But yeah, so what you need to find is the order statistics for uniform distribution. Uh, okay, so uh, we'll do the proof first. So, okay. So what you want to find is probability of Pi less than or equal to Si less than or equal to Ti plus delta Ti. This I is for all n's. So, I'll write down what I'm saying. Conditioned on n t equal to n. So now I know that in time t, n events have occurred. That is my conditioning. So the thing that I know is nt equal to n has occurred. Uh, so n events has occurred. Yeah, and now what I'm doing here is, uh, so suppose I have n events. Yeah, what I'm doing here is I'm taking a small interval for each event that has occurred. And now, as you can see, these intervals are all non-overlapping intervals. I take those intervals so small that they're non-overlapping. These TIs and TI plus delta I's are basically those. So next what I do is I write this as probability of exactly one event in Ti comma Ti plus delta Ti and no events everywhere else in 0 to t, right? By probability nt equal to n. So now what I've done is I want to find the probability of one event happening in this interval, one event happening in this interval, one event happening in this interval, one interval in this, and in the total time t that I've given, I know that only n have occurred, and that I've written down here. So these all remaining the remaining everywhere else other than the intersecting part, no event should occur there, right? So uh, the probability of exactly one event occurring is and since all the events are disjoint, so they're non-overlapping. The intervals don't overlap. You can use the independent property of non-overlapping intervals. You can use a and product. You can write the probability as products. So you'll have yeah. So the first is one event happening in delta T. Sorry, one event happening in delta Ti. So you have lambda into delta Ti e power minus lambda into delta T1 into lambda into delta T2 into e power minus lambda into delta T2. So on lambda into delta Tn e power minus lambda delta Tn. So These all are probabilities. This is the probability for one event happening in between S1, one event happening between S2, one event happening between Sn, and then you have no no event happening elsewhere else. Now you need to calculate the total interval time that. So let us take. You need to calculate the total interval where nothing has happened. So where nothing has happened, the length would be t minus, since the total length is t, and the small intervals are delta t1, delta t2, t minus summation of delta ti's, I equal to 1 to n. This would give you the length of the intervals in red. They are also again non-overlapping. So you can just write it as e power minus lambda into t minus summation I equal to 1 to n lambda I, by probability of n t equal to n is e power minus lambda t power n divided by n factor. Now, what you have here is you have n lambdas. So this is one lambda, this one lambda. Similarly, you have n lambda, so you have lambda power n. And then if you write all the exponents in one term, you get e power minus lambda delta t1 plus delta t2 plus delta 3. So this is basically sum over I equal to 1 to n delta ti. This is delta ti. Then you have e power minus lambda into e power plus lambda summation I equal to 1 to n delta ti. These both cancel out. And what else are remaining? All the deltas are remaining. So delta t1, delta t2, so on, delta tn by e power minus lambda t, lambda t power n by n factorial. Lambda power n gets cancelled. E power minus lambda t, e power minus lambda t gets cancelled. Now what you have just remaining is n factorial by t power n into delta t1, delta t2, so on, delta tn. Now what you do is you take this delta t1, delta t2, delta t3 to the other side, and you get probability of Si less than or equal to t less than or equal to ti. Okay, let me read properly. Probability ti less than or equal to Si less than or equal to ti plus delta ti for I equal to 1 to n, conditioned on nt equal to n. This was the original left hand side of the equation, divided by delta t1 into delta t2 into so on delta tn. This is equal to n factorial by t power n. Now, if you take limit delta ti tends to 0 for all of them, what you'll get is you'll get the density function delta t1 to tn, not the distribution, the density function as n factorial by t power. So you can see that this is the order statistics distribution of n random variables which follow the uniform distribution. So what I'm saying is if you have x1, x2, and so on till xn, these are IID and they have uniform distribution. Between 0 and t. So now then the distribution of x1 would be 1 by t, right? Similarly, the distribution of x2 would be 1 by t, same. Just the length of the interval into 1 by t. This is the density function of all those. Now the joint density x1 till xn would be just the product of those because of independence. They are independent random variables. But now I want the distribution of the order statistics of uniform random variable. So order statistics would just be n factorial by t power n. which is the same as the um, uh, arrival times distribution conditioned on the number of arrivals that have happened at time t. Okay, so I hope the proof is clear. So yeah, why do we need this is, okay, I'll do an example such that, so example problem so that this theorem gets used and you understand where we use this kind of. So suppose there is a train depot. Passengers arrive to this train depot to board some journey. They arrive at a Poisson process with rate lambda. If train, now we know that train departs at time t. One train departs at time t. So at time 0, people start coming with the Poisson process with rate lambda. We know that the train departs at capital at t. Now, what we want to find is we want to compute the expected sum of waiting times of all the travelers that arrive between 0 and t. So we want expectation of summation I equal to 1 to nt. So nt is a number which gives you the total number of passengers that have arrived till time t minus si. So basically what I'm saying is, suppose a person has arrived here. So this is S1. The waiting time of the person S1 to catch the train would be T minus S1. This is the amount of time that he has to wait in the train depot so as to catch the train. Suppose a person has arrived here, S2, second person. T minus S2 is the waiting time for the S2 person to catch the train. So you're basically, you want the expected sum of waiting times of all the passengers that have arrived there. So basically you want this term, expectation of sum of waiting times. These are the waiting times of nt, a random number of passengers that have arrived till time t. So to do this, first what we'll do is we'll condition it on. So suppose nt is a random variable which takes a natural number, but we'll condition it on that we know what that natural number is. So basically we'll first find expectation of summation I equal to 1 to nt t minus si condition on nt equal to n. So this basically boils down to expectation of summation I equal to 1 to n. Now, because I know nt equal to n, t minus si, but the condition doesn't go away because you have just replaced nt with n, but it is still conditioned on the fact that you know that n arrivals have happened in nt. So now I can use linearity of expectation or conditional expectation. And separate out expectation of summation I equal to 1 to n conditioned on nt equal to n minus expectation of summation I equal to 1 to n si conditioned on nt equal to n. Okay. Next we have, so here there is nothing random here. So expectation of a deterministic term is just deterministic. So this is basically nt minus expectation of summation I equal to 1 to n si given nt equal to n. Now we need to calculate this term. So expectation of, again by using linearity. Oh yeah, I don't think you need to use linearity. Okay. Summation of I equal to 1 to n si given nt equal to n is equal to the distribution expectation summation I equal to 1 to n the order statistics of uniform distribution. This is from the previous theorem. So suppose, what I'm claiming here is I know the joint distribution of S1 to Sn. Now let U1 be the to UN, this be the joint distribution of the ordered statistics of uniform random variable. So these both are equal. So then what we're finding is expectation of g of some function of S1 to Sn. This is equal to expectation of finding the same function over the order statistics. So because they both have the same distribution, so finding the expectation of a function of all these random variables is equal to finding the expectation of the same function with these random variables. But the equivalence of the distribution is conditioned on the fact that you know that at NT interval, n number of variables have occurred. So expectation of summation of I equal to 1 to n Si conditioned on NT equal to n is basically the expected sum of ordered statistics of n independent uniform random variables distributed over 0 to t. This is from the theorem that we've just proved. Now, we see that the sum, you change the order, the sum remains the same, nothing changes. So the distribution of sum of ordered random variables is equal to the sum of just the normal random variables, because 1 plus 2 plus 3 is basically 2 plus 3 plus 1. You can change the order, the sum remains the same, the sum doesn't change. This is basically I equal to 1 to n ui. This is because summation ordered statistics is equal to summation ui. So we know that again, you can use linearity expectation summation I equal to 1 to n ui. This is linearity of expectation. Expectation of uniform is t by 2, the half of the interval. So you have n into t by 2. Now you need to substitute this back to. So let me. You need to substitute this back here. You need to substitute this back here. So what you have is expectation of summation I equal to 1 to nt t equal to n equal to nt minus nt by 2, which is just nt by 2. Now, now to go from here to expectation of summation I equal to 1 to nt minus si. What you can t minus si, what you need is you can calculate the expectation of this in which is okay, maybe I'll write it down again. So expectation of what you're doing is this is known as a tower property of conditional expectation. So suppose you have some random variable conditioned on some event nt equal to n. You can just basically take the expectation again and just say that it is the expectation of the random. This is known as a tower property of conditional expectation. I think this we showed in the we use this in the introductory class. So yeah, so just calculate the expectation again. And now here the randomness is in n. The number of arrivals that happen in an interval, that is the random. So you're taking expectation over that random thing. Here n is not deterministic. So the expectation of the expectation would just be expectation of nt into t by 2. So here we are using the tower property. And then you get that expectation of summation I equal to 1 to nt t minus si is basically this. You know that the expected number of arrivals in the time interval t is lambda t into t by 2. So expected waiting time is lambda t square by 2. So this is one way to calculate how much sum of expected times. So here you can see that we always worked on SI, the arrival times, but because of the theorem, it became easy for us to change the distribution from SIs, from Erlang distributions to uniform distributions, conditioned on the fact that n number of arrivals has happened. So we do it for nt equal to n, and then we randomize n. We take expectation again and randomize it. So this is one of the examples where uh, we found what is the expected uh, waiting time for the passengers that come to board a bus or a train. So this is the so next what I'll be doing is okay. So okay, I'll do one more example. Okay, so this example. Suppose okay. Okay, suppose there's a device. Now what happens is this device is subjected to some shock from some external shock or force applied on this device, but the time at which external force is applied is random. So at random moments, random forces are applied on this device. And once a force is applied on the device, each force gives rise to some random damage, which I call it as di. So ith force applied on the device would damage the device di. So what I'm saying is, let this be the time scale t. So suppose the first force that occurs on the device occurs in S1 here. So this will give rise to a random D1, some amount of damage the device would take, or some amount of deformity the device would take. And once the force has occurred, the deformity would keep on decreasing exponentially. That is the question. So so it keeps on decreasing exponentially. It need not decrease full to zero. Then suppose some S2, another force has been applied. Again, random. These are random. So suppose some random D2. Now D2 is from here to here is D2. It takes D2 amount of force, additive. The damage is additive, but it will keep on decreasing exponentially. Suppose S3. S3 here, another damage has occurred, but now it's less than the previous one, and it will keep on decreasing exponentially. So what we want to find is what is the expected damage that has occurred to the device till time t. Suppose this is time t. We want to calculate the expected amount of damage that has occurred till time t. Okay, so let me formally write it down mathematically. So di is the damage event that occurs, and di occurs independently and identically, and it's a Poisson. It happens at Poisson distribution. Um, so suppose d1 is the initial force that has been applied on the device. Then at time t later, the damage would be d e power minus alpha t. This t is after t time, after amount t, the damage would become d1 into e power minus alpha t. And now I say that dt, the total amount of damages that has occurred in time t is summation I equal to 1 to nt di e power minus alpha t minus si. So basically what you're doing is, so you have T, you have T and again T and multiple times T. So now suppose the first damage has occurred here. This much amount of damage has been caused. It will decrease exponentially. Next, suppose here a damage has occurred. This will also decrease exponentially. But we are only interested in time t because we want to find the expected amount of damage that the device has occurred till time t. The nth will have occur here and it will like die down till time t. So basically, we are interested in the damage that this point at this point that the device is facing. So sum of all these. So the damage at this point would be d1 e power minus alpha. This is s1. The whole thing is t. So the damage is felt till t minus s1. Here at this point, the damage that the device or deformity that the device occurs is d2 e power minus alpha t minus s2. So basically, you can think of this as you have a sponge, the device is a sponge, you apply some force, it deforms, and it slowly, when you release the force, it slowly comes back to the original position. The coming back to the original position is exponential. Now you want to find at time t what is the expected deformity of the sponge because of this random forces that you're applying on the sponge. Okay, I hope the problem statement is clear. And what we're trying to find is expectation dt. So we'll do it in the same way that we did the previous problem. We'll always condition it on nt equal to n. So we know that n number of forces have acted on the sponge till time t. So the total is summation I equal to 1 to nt di e power minus alpha t minus si condition on nt equal to n. The same, we'll interchange nt with n di e power minus alpha t minus si, but the conditioning remains because the conditioning is what makes nt is nt equal to n. Now we'll apply linearity. Let me write linearity. So linearity property, what you can do is you can exchange the summation and the expectation. That is one property of expectation. So summation expectation di e power minus alpha t minus si conditioned on nt equal to n. Okay. Now, so you have two terms. This is one term and this is one term where both randomness are present in both the cases. So DIs are also random and SIs are also random, but they both are independent. So what amount of shock happens in the ith instant is independent of when the ith force has happened. So you, from the independent property of expectation, you can write this as a product. This is basically expectation of D. This expectation of D is different from expectation of dt. This expectation of D is basically the distribution that the D's are distributed with, the expectation of that distribution. It's not the expected damage that the device has seen till time t. This is something that we know. We know the distribution in which D is defined. And then summation I equal to 1 to n expectation of e power minus alpha t minus si condition on nt equal to n. Okay. And here you can see e power minus alpha t also is deterministic. So you can bring that out also, expectation d into e power minus alpha t. And then again applying linearity, you can take the summation inside I equal to 1 to n e power plus alpha e power alpha si conditioned on nt equal to n. Now, this again, the similar way that we have done before for the theorem. So we know that the distributions of S1 to Sn can be is same as the distribution of the ordered statistics of uniform random distributions. So basically, I'm now trying to find this term. So this term, expectation of summation I equal to 1 to n e power alpha si conditioned on nt equal to n is equal to expectation of summation I equal to 1 to n e power alpha u order statistics where ui's are order statistics of uniform IID random variables distributed between 0 and t. But it doesn't matter, the summation of exponential of whatever order you do e power alpha ui, the it remains same. So this is basically summation I equal to 1 to n e power alpha u I n t equal to n. Now this term is basically the exponential okay, there is no conditioning. There is no conditioning because you know that the distribution is uniform. You integrate it over 0 to t e power alpha x dx, and you get n. So this is the function e power alpha x, and there are n terms. N are identical, so you get a product of n, and 1 by t is the density function for uniform random variable. T doesn't depend on this, so it comes out. So you get n by alpha t e power alpha t minus 1. Then expected dt given nb equal to given nt equal to n. This is n by alpha t. E okay. Here you have a e power minus alpha t. So it multiplies with e power alpha t, you get 1 minus e power minus alpha t and expectation of t. Similarly, the expectation of dt is lambda into t, because now you replace this with expectation of nt and you get lambda t by alpha t 1 minus e power minus alpha t expectation d. T cancels, you have lambda by alpha the minus alpha t expectation d. So yeah, this is the expected deformity that the sponge sees in time t. So these are some of the problems that you will face while doing Poisson process. So yeah, I'll stop the lecture for today. Next class, I think we'll continue. We'll do non-homogeneous non-homogeneous Poisson. Hello, yeah,
Okay. Okay.
yeah. So I'll stop the recording. Yeah. So next class.